example here. I think it's this example. So I didn't have it written down.
4x cubed
4x cubed.
minus 12x squared plus 5.
Let's see how my camera's set up here. Okay, so we're gonna finish this example. I guess I gotta move that bad boy over a little bit.
Oh, dang it.
Is it a different one?
Yeah.
Okay. So what's it supposed to be?
X to the fourth minus 2x cubed. Yeah.
Don't ask me.
And nothing else on it?
That was just also true.
Okay, so our overview is this. We are looking for where this thing has critical numbers. And that's where the derivative is 0. It won't be undefined because it's just a polynomial. But for typical functions, it's where the derivative is 0 or undefined. Then we're looking for intervals on which it's increasing and which it's decreasing. The first derivative tells us that. Where the first derivative is positive, the function is increasing. Where the first derivative is negative, the function is decreasing. Then we're looking for a relative max and a relative min. Again, we can use all of that by looking at the change in sign of the first derivative. If we get a critical number and the first derivative rises and then falls, as we read from left to right on the number line, that critical number is a max. If we get a critical number and the function decreases and then increases as we read left to right, then the critical number is a min. That's called the first derivative test for relative extrema. Then we're going to look for where this thing changes concavity. The point at which the concavity changes is called an inflection point. So that's where the second derivative is 0 or where the second derivative fails to exist. Again, we've got a polynomial, so we're just going to look for zeros. It's going to be concave upward wherever the second derivative is positive. It's going to be concave downward wherever the second derivative is negative. Okay, so f prime positive implies f is increasing. F prime negative implies f is decreasing. F double prime positive implies f is concave up. F double prime negative implies f is concave down. So that's the big picture. So we want to try to do that for this particular function. Oh, the camera in the wrong spot. Let me back it up a bit. Oops, wrong way. I gotta move that camera and it's probably gonna unhook. Maybe I'll just leave it right there. Okay, so we took the first derivative. We got how many critical numbers? 2? We get 4x cubed minus 6x squared. Right, and I pulled out a 2x squared. And that leaves us 2x minus 3. And so our derivative is 0. When each factor is 0, 2x squared is 0 only when x is 0. And 2x minus 3 is 0 and x is 3 halves. So now we analyze the sign of the first derivative. Put those in order on the number line. And I want the sign of the derivative. So I'm looking here at the factored form. And the sign of the derivative again tells me the direction that f is moving. I just gotta lift that a little bit. Let's see if it shuts off. Shut off. Coming back at you, hang on, I hope. Okay, we're back. I just had to move the camera a bit. Person, can you hear? Is there audio?
Yes, I can hear.
Okay, great. We're set then. All right, we'll keep going then. So we're going to plug numbers in to the derivative to get the sign of the derivative. And what we noticed before was that no matter what we put in for x here, this first factor is positive because it's squared. So really, we just test the sign of 2x minus 3. If x is a -1, I can get a -5 out of that. If x is a +1, I'm still negative. But then if x is +2, that becomes positive. So the direction of the function is that it drops, briefly has a 0 slope here, and then it keeps dropping, and then it's going to rise. So now we can answer the first 5 pieces here. Our critical numbers are x is 0 and 3/2. It increases when that arrow's pointing up, so that's to the right of 3/2. And it decreases to the left of 0. And then again, between 0 and 3/2. It's doing neither at 0. At x is 0, the tangent line is horizontal. Since the graph never changes direction in the way of a maximum, we have no relative maximum. But we do have a minimum at that critical point where it turned around there. At x is 3/2. Hits the 3/2, comes back up. So right now we think that the graph looks kind of like a parabola. Except for somewhere in there, the tangent line gets horizontal. We'll see that change in concavity to emphasize that. Now we do everything that we did with the first derivative, but we do with the second derivative. So our second derivative is 12x squared minus 12x. We're going to set that equal to 0. So as I do that, I pull out a factor of 12x. And the other factor is x minus 1. Set each factor equal to 0, and you'll get from the first factor, x is 0, and from the second factor, x is 1. Those are the 2 inflection points. So it's okay if a critical number is an inflection point. Now we analyze the sign of the second derivative. So make a number line. And we're going to put 0 and 1 on here. And we're looking at the sign of f double prime. And again, I'm going to use its factor form. And it tells us the concavity. So if I stick in a -1, my first factor will be negative, my second factor will be negative, and the negative times the negative gives me a positive. If I stick in a 1/2, the first factor is positive, but the second factor is negative. I get a negative second derivative. And now when x is 2, both factors are positive. So my second derivative is positive. So the graph is concave upward where it's positive, concave downward in the middle. Let's write those as intervals. Concave upward to the left of 0, from -infinity to 0, and then again from 1 to infinity. Concave downward in between. So from this information, it gives us a pretty good graph. We might want to plot the points that are of importance to us, the 2 critical numbers and the 2 inflection points. So let's go back, we're graphing this, so that's where we plot everything. So to get the graph, some points. We need f of 0. That's easy enough, that's 0. F of 3/2. 3/2 to the 4th power. I guess I better write it. I'll do that in my head. Minus 2 times 3/2 cubed. That's, I said. Just change that to a half. Let's see, 3 to the 4th is 9 times 9 is 81. 2 to the 4th is 16. 3 cubed is 27. 27 times 2 is 54. 2 cubed is 8. So if I get a common denominator, -81 minus 108 is a negative 27 over 16. Close enough? I believe. Yeah, sucker. F of 1 is the inflection point. 1 to the 4th minus 2 times 1 is -1. So I'll see if I can fit the graph right up here. Right up here. So let's say everything is happening over here. So let's just kind of most of the graph there. It goes through 0, 0. Let's make a big scale here. Let's put this at 1, and that's 2. So 1, we're down 1, 1, 1. 1, we're down at -1. And 3/2, which is in here, that's -1-ish, so it's down here. Okay, so now we had a horizontal tangent line when x was 0. We had a horizontal tangent line here. This was just an inflection point. We have our graph going down, down, up. So we're going to go down, down, and then up. But we have to do it in such a way that it's concave upward over here. In between 0 and 1, it's concave downward. And everywhere else, it's concave upward. So let's make it decrease, but be concave up. So we're going to turn it up a little bit. Follow the dotted line, but make it concave up. Flatten it out as if it's going to be a parabola. But then it changes its mind, and from here to here, it's decreasing and concave down. Like that. And then everywhere else, follow the dotted line and make it concave up. Okay, so it looks like it started out as a parabola, but somebody punched it right there in the gut. And that's the help that the second derivative gives us in sketching the graph. So we find changes like that. Pretty cool, huh? All right, let's take the derivatives of harder looking functions. Let's do all the same stuff, but let's use f of x is equal to x squared times e to the negative 3x. Same thing for f of x is x squared e to the negative 3x. We want the critical numbers, increasing, decreasing, relative max and min, and the inflection points. So I'm just going to erase all this part and leave my stuff over here. So before you start taking derivatives, recognize that both x squared and e to the x are always continuous. So we're not going to have any sharp corners or places where the derivative fails to exist on any of our derivatives. They're all going to be critical numbers, and inflection points will be where the derivatives are 0. So in order to do this first part, you'll need the first derivative. Take a look at it. You're going to need to take the first derivative using the product rule. So knock that out while I erase the board. And try to take your first derivative and factor it. You're going to get two critical numbers. First derivative with the product rule. Derivative of e to the negative 3x is negative 3e to the negative 3x. Then we're going to take the derivative of the power. And then the derivative of the x squared gives me the 2x. So when I set that equal to 0, I'm going to try to factor out the common factors. Both of them have an e to the negative 3x, and both of them have an x. So let's pull out x e to the negative 3x. I've got one of these x's left, and I've got a negative 3 left. And then I pull that x out, and I pull the e to the x out, so I got a 2 left. So really, I have 3 factors, but only 2 of them have a chance of being 0. E to a power is always positive, so it's never 0. But I get in a critical point when x is 0, and when negative 3x plus 2 is 0. So if I subtract 2, divide by negative 3, cancel the negatives, I get x is 0 and x is 2/3 as my 2 critical numbers.
What did you say about the e to the negative 3x? I think
E to the power is always positive. Any exponential function is always positive, never crosses the x-axis. Right, remember what an exponential function looks like? Either that or that, but both of them are above the x-axis. I'm not going to cross. E to a power is always positive. Just like 10 to a power is always positive. 2 to a power is always positive. All right, now we're going to look for increasing and decreasing by subdividing the number line around 0 and 2/3. And we want the sign of f prime. And that's going to tell us the direction of that. Again, this is always positive here. No matter what x is, it's always positive. So I just use the first two factors. So let's imagine that we're putting in, say, a -1 for each x. It gives me a -1 here. This gives me a +5 here. And so I get a negative derivative. Now I guess we could use something like 1/3. If x is 1/3, that's positive. -3 times 1/3 is -1, plus 2 is positive. Positive times a positive is positive. And then if x is 1, we got positive, positive, negative. So the graph drops, rises, drops, and we have both the max and min. See how the critical number at 0 is going to be a min? The critical number at 2 is going to be a max. So it increases between 0 and 2/3, decreases to the left of 0, and then again to the right of 2/3. Relative max, we said, was at x is 2/3. Relative min was at x is 0. Are you good with that? Okay, well, we got to find a nice place to take our derivative again. The second derivative can be messy because we're going to have a product rule within a product rule, aren't we? See if we can handle the second derivative. Do the first times the derivative of the second plus the second times the derivative of the first. But when it comes time to take the derivative of the first, you got a product rule right there. Let me give you a minute to try that. Let me see if I get the same derivative as you. So the first is x e to the -3x. The derivative of the second is just -3. Now the second, -3x plus 2 times the derivative of the first, but we do another product rule. So here's x. Now the derivative of e to the -3x is itself times the derivative of the power. Then the other way, e to the -3x, the derivative of the x is just 1. I think I'll multiply everything out and then try to factor it. So when I multiply this out, I have -3x e to the -3x. When I multiply this, that gives me plus 9x squared e to the -3x. The first times the last gives me minus 3x e to the -3x. Inside terms give me minus 6x e to the -3x. And finally, the two last terms give me plus 2 e to the -3x. And so I can put this one, and that one all together. And get a negative 12x e to the negative 3x. But before I do that, I'm gonna factor out e to the negative 3x and then do that inside. So I'm gonna have a 9x squared. And I say that was gonna be a negative 12x plus 2. Something close to that? I doubt very much that polynomial factors. So when we're looking for inflection points, we're gonna have to use the quadratic formula here. Exactly, parentheses equals 0. You wanna ask something?
I was just, confusing how you got to- how you factored out the-
Were we okay with the derivative?
or not that part.
But you're okay here?
Yes.
Okay. And so when I multiplied it out, everything here has to e to the negative 3x on it. So I pulled it out. So pretend we erase all those. And then the ones underlined all have an x. So I added those together and got me to negative 12. This has the x squared. I wrote it first, and that doesn't have any x's. So I'm setting the batch in parentheses equal to 0, and I'm going to use the quadratic formula. X is equal to the opposite of b, so that gives me a 12, plus or minus b squared. 12 squared is 144, minus 4 times a times c, so times 9 times 2. That's in the square root. All of that's over 2 times a. 2 times 9 is 18. So let's see. 8 times 9 is 72. 72 from 144 is 72. Let's see, 72 is 9 times 8. 8 is 4 times 2. 4 times 9 is 36. So 72 is 36 times 2. So let's write square root of 72 as 6 square root of 2. And then both, all three, 6, 12, and 18 are divisible by 6. So let's cancel 6 everywhere. So x is equal to 2 plus or minus the square root of 2 all over 3. 2/3-ish, right? I have those as decimals somewhere. Let's see if I work this out, I've got decimals for these. The smaller one is about 0.2, and the bigger one is about 1.1. Kind of need to know that because I've got to plug some numbers into this thing here, see where this is positive or negative. Let's put 0.2, 1.1, and we're looking at the sign of F double problem. So e to a power is positive. I really don't need to worry about that. Let's just pick a number and see what happens in here. So I can use 0. If x is 0, all of that is positive. Here I could use x is 1. 9 plus 2 is 11. 11 minus 12 is going to be negative. And then here I'll use x is 2. 4 times 9 is 36. 36 minus 24 plus 2 is positive. So it changes concavity. Concave up, concave down, concave up. So back over here to where we asked about the inflection points and such. I've got inflection points at 0. I'm sorry, at 2 minus the square root of 2/3 and 2 plus the square root of 2/3. It's concave up to the left of the smaller one. So from minus infinity to 2 minus the square root of 2/3. And then again to the right, 2 plus the square root of 2/3 to infinity. Concave down in between. So I'm not gonna plot those points. I don't care where they are, I'll take those. Let's plot these two back in here. F of 0 is gonna be 0. Okay. So I'm just kidding. It'll be 0 times 1, so it'll be 0. And then F of 2/3 will be 4/9. Put 2/3 in here and I get e to the -2. So those are the 2 points I'm going to plot. And we'll figure out where the other ones are. So let me find some room where I could do that graph. Let's do the graph right up here. So another thing I want to point out, x squared is always positive, at the very worst it's 0, right? E to the -3x is always positive, it's never 0. So this graph lies entirely above the x-axis, or it's going to hit 0. So I can put the x-axis here, and then the y-axis here. Goes through 0, 0, but it doesn't pass through it. And then I've got 2/3, 4/9 something something. I have that as a decimal. I don't. Well, let's just put it right here. Then, where's my red pen? Let's draw the horizontal tangent line on the 2 critical numbers. 0 and here. Then we got to draw a graph that drops, climbs, and drops. It's going to drop and not cross this axis here. So that's where the 2 inflection points come in. We've got 2 of them. One's about 0.2. 2/3 is 0.7, right? So we've got an inflection point about right here. And then the other one was 1.1, so if that's 0.7, let's just use symmetry and put 1.1 here. That's where the concavity is going to change. According to this, we have to draw it concave upward all the way here, concave upward until we hit that inflection point, then concave downward here, then it has to become concave upward. It's this piece turning concave upward that's going to keep it from crossing the x-axis. So it's going to look something like this, or blue. So concave upward, follow the dotted lines right in here, concave up. Great. Now make it concave downward between the two inflection points and follow the dotted lines. And now it's going to decrease but be concave up. So it's going to have kind of an asymptote out here. Continue to decrease but be concave up. It's another pretty graph. Right, you could have drawn that graph in your pre-calculus class. You need to know some calculus to figure out what the shape of it is. And even a graphing calculator wouldn't help too much because the scale is so small. Those are all very small numbers. You have to really zoom to see this thing on a graphing calculator. I bet you wish I had another one.
Yeah.
Well, lucky you, I do. You've been wanting to do the quotient rule. Let's do the quotient rule. Let's do all the same stuff for x divided by x squared plus 1. X divided by x squared plus 1. So do the quotient rule on your first derivative. It's going to take some simplifying. Make sure you can simplify it enough to get you 2 critical numbers. They're going to be nice whole numbers. So not 2 nice whole number critical numbers after you simplify that. Got them yet? 2 critical numbers, anybody? Bottom times the derivative of the top minus the top times the derivative of the bottom over bottom squared. So what did your numerator simplify to? Apply that out, like terms, what'd you get?
X squared plus 1.
Negative x squared plus 1. All right, that is 1 minus x squared. Okay. So a couple things I want to point out. X squared plus 1 is never 0. Great. Square something, it's positive, add something, keeps it positive. So I'm never dividing by 0, which means this function is defined for all values of x. If x squared plus 1 is never 0, neither is x squared plus 1 squared. So the only critical numbers come from where the numerator is 0. So f prime is equal to 0 when 1 minus x squared is 0, and that's when 1 is x squared. There are two numbers that do that, plus and minus 1. Or you could factor 1 minus x squared is 1 minus x and 1 plus x. You get two critical numbers there. Okay, 1 and negative 1. Now let's check the sign of this thing. Let's put our number line right here with negative 1 and 1 there. And we're looking for the sign of f prime. Tell me about the direction of f. And I don't have to test anything in the bottom because the bottom is all that stuff squared, so that's positive. That's not going to affect the sign. So really just plug numbers here and see what the numerator is. If x is negative 2, I have 1 minus 4, so that's negative. Same thing happens when x is positive 2. When x is 0, I get a positive in there. So my graph goes down, up, down. So I write that it increases only between negative 1 and 1. Decreases to the left of negative 1. And then again to the right of 1. Which one's the max? X is equal to 1. And then this is at x is negative 1. Here comes the fun part. We're going to take the second derivative using the quotient rule. We're going to take the second derivative. I'll help you simplify it. Bottom times root of the top minus top times root of the bottom over the bottom squared. And then I'll show you how to simplify. Top is a negative 2x. All right, your derivative should look something like that. Got all those pieces? Now, instead of multiplying things out, I noticed that my numerator has only two terms in it, before the minus sign term and after the minus sign term. And both of those have x squared plus 1 in it. At most, they have it to the first power. So I'm going to knock 1 power of x squared plus 1 out everywhere. So this becomes to the first power. This one's now gone. And this is now to the third power. And now I'm going to multiply out my numerator with what's left. So this is to the first power. I can send the negative 2x through the parentheses. And I'm going to get negative 2x cubed minus 2x. Back here, I have this 2, this 2x to give me 4x, and I'm going to send that through this parentheses. So 4x times 1 gives me a 4x right here. 4x times negative x squared gives me negative 4x cubed. We're going to keep the bottom factored. So in the next step, I'm going to remove the parentheses, distribute the minus sign, and collect like terms. So let's look at the x cubed terms. I have a negative 2x cubed plus 4x cubed. gives me a positive 2x cubed. Then I have a minus 2x minus 4x to give me a minus 6x. That good for you? We're looking for inflection points, so they're going to come from what makes the numerator 0. Because again, I can't get x squared plus 1 ever to equal 0. So I'm going to factor out a 2, and I'm going to factor out an x. And that leaves me x squared minus 3. Shouldn't the bottom still be cubed? Thank you. Good there? I got 3 inflection points. Can you tell me what the 3 inflection points are? 0 is one of them. Plus and minus the square root of 3. You get plus and minus the square root of 3 by setting this equal to 0. And you get x is 0 by setting that equal to 0. So our inflection points are 2x is 0 when x is 0. X squared minus 3 is 0 when x is plus and minus square root of 3. So let's cut the number line into 3 different pieces and look at the sign of our second derivative. So let's see, negative square root of 3 be the smallest, then 0 and square root of 3. Okay, so f double prime is 2x, x squared minus 3, x squared plus 1 cubed. Do. There we go. Okay, so we're going to plug numbers in there. X squared plus 1 is always positive, so we're going to ignore the denominator. That's always positive. Let's plug numbers into the top. Square root of 3 is about 1.7. So if I put in a negative 2 here, that's a negative 4, and that's a positive 4 minus 3. So I get negative times positive over positive. That's going to be negative. I put a negative 1 in there. This first factor is negative, so is the second. 2 negatives multiply to a positive. I put a 1 in there, I get a positive, negative. That's going to be negative. You put a 2 in there, and everything's positive. So the negative second derivative indicates concave downward. And the positive second derivative indicates concave upward. Concave up between negative root 3 and 0. And then again between square root of 3 and infinity. Concave down to the left of negative square root of 3. And then between 0 and square root of 3. Okay. All right, we're going to plot our max and mins. F of 1 is a half. F of negative 1 is negative a half. And we'll figure out where the other ones are when we're graphing. But 1 is a half of negative 1 is negative a half. Let's get the graph right here. So f of 1. F of 1 is a half. Let's do it there. And -1 is down, -1/2. At those two places, the derivative was 0, so put a horizontal tangent line there. X is 0 is an inflection point. Let's plot that. That one's easy enough. That's an inflection point there. Now I got to figure out what those other inflection points are. I said square root of 3 is about 1.7. If I put square root of 3 in for x, I get the square root of 3 over 4. So that's almost a half, but smaller. So let's put that, put our inflection point. If that's 1, that's 2. Let's put our inflection point. So it's almost a half, so let's put it here. Well, let's do another one over here. I suppose the other one's going to be negative, and it is. So let's put it about right here. Okay, so we've got to make the graph drop and hit -1. So let's go drop and hit -1. Rise up until it hits 1. And then drop for the rest of the way. Then we have to make it do the concavity that it does here. Concave down over here. Concave up between that inflection point and that one. Concave down between that inflection point and that one. And concave up beyond that one. Here's where we pull out the blue. It's going to be decreasing but concave down. So decreasing but concave down. Concave up between the two inflection points. Concave down between the next two inflection points. And then concave up. I kind of lied on the ends of that graph. We'll talk about asymptotes in the next section, but what happens to the ends of the graph is that I've got a horizontal asymptote at y is 0. So this one's going to bend toward the axis without ever crossing it. In reality, it looks like this. Stretch this out, take that away. It looks like this. We've got a horizontal asymptote there. Same deal is going to go on over here. And I'll show you why we have a horizontal asymptote when we finish this next section. And if you cover horizontal asymptotes in pre-calculus, you can kind of look at the degree of the numerator and denominator to tell where the horizontal asymptotes are. We'll talk about that after you guys take a little break. Don't you want a little break? Go stretch, walk, scream, holler, yell, run. Uh-oh, husband agreed to the dog thing. Looks like I got a dog. Don't you forget you promised to dog sit for me. 2. Oops, sorry.
Yeah, it's good.
So, to be honest, we sat twice a day one time and then still went back the next day and I didn't get to return. My friend tried it and she said it's good.
I can't believe you guys are talking about food here in front of me.
It's like red something. And it was so good. The grilled chicken. We're torturing ourselves. Yeah.
It's like there was the smell of cookies wafting through the air. Now, one more bit in section 4.3 before I jump to 4.4. So the last thing in section 4.3 is we're going to have yet another way to determine whether a critical number gives you a relative max or min. We already have the first derivative test where we plug in test points around each critical number to look at the direction of the graph. If we're not interested in graphing, then sometimes it's quicker to tell whether a critical number gives a max or min by looking at the sign of the second derivative. And that'll be called the second derivative test for relative extrema. So this is the last bit of section 4.3. The second derivative test. Relative extrema. So the same requirement is that if a function has a relative max or min, it has to occur at a critical number. So let's let x is equal to c be a critical number for some function y is f of x. If we find this critical number, and then instead of doing the number line and checking the sign of f prime, we just hang on to it, calculate the second derivative. The second derivative tells us concavity over intervals. It can also tell us the concavity at a single point. If I take my second derivative and plug in my critical number and get that my second derivative is positive at that critical number, then it has to be positive in an interval that contains the critical number. Well, second derivative positive means it's concave up. So the critical number is going to have to be down here and be a relative minimum. If I plug in this critical number into the second derivative and get a negative value, that tells me the graph is concave down there, and that critical number is going to be a relative max. So if f double prime evaluated at the critical number is a positive number, then the graph is concave upward. So we have f at c is a relative min. If the second derivative evaluated the critical number is a negative value, that means the graph is concave down. So f of c is a relative max. It's easy to remember if we make a picture out of this. I'm taking two derivatives and I get something that's concave up because it's positive. So I'm going to use this as a smile and put two plus signs here. Second derivative is positive, it's concave up, so it's a min. Here I got two derivatives and it's negative, so I'm going to use minus signs. That makes a sad face. So it's concave down, and you got a max. We're going to use the second derivative test a lot when we're not interested in graphing. We're going to do some word problems in section 4.6, and we're only going to be interested in where the company has the largest profit, or where the area is a maximum, or where the cost is a minimum. So we don't care about the graph, we just want to know the sign of the second derivative. So let's get a bit of practice here. Show that x is equal to pi halves is a critical number of the function f of x is equal to the sine of x plus 1/2 of the cosine of 2x. Show that it's a critical number, And then determine if it's a max or min using the second derivative test. Now this function is going to have a lot of critical numbers because it's a trig function, so it does all that. So I'm not asking you to find all critical numbers. Just show me that pi halves is a critical number. In other words, take the second derivative, plug pi halves in for x, and I'm sorry, take the first derivative, plug pi halves in for x, and show that the first derivative is 0 there. Okay, so for this part, just show that f prime at pi halves is equal to 0. So let's do that together. Call me out the derivative. What's the derivative of the sine of x? Right. Now I'm going to write down the 1/2 and tell me the derivative of the cosine of 2x. Negative sine of 2x times 2. 2 comes from the derivative of the angle there. So I can go ahead and put the 1/2 of the 2 together and then put the minus sign. So I've got f prime of x is the cosine of x minus the sine of 2x. That's kind of a hard equation to solve anyway. If you're going to try to solve for the critical numbers yourself, you have to whip out a double angle formula. But let's put pi halves in for x. We need to know the cosine of pi halves. And 2 times pi halves is pi, so we need to know the sine of pi. Do you know any of those values? What's cosine of pi halves? Nope. Pi halves. Pi halves is 90 degrees. 0. What's the sine of pi? Cosine of pi is -1. 0. So I get 0 minus 0. There you go. It's a critical number. Okay. Now we're going to take the second derivative. So for our second derivative test, it only makes sense that we need the second derivative. Derivative cosine of x is minus the sine of x. Then I have the derivative of minus sine of 2x, and I'm going to get minus 2 cosine of 2x. Now we're just going to plug our critical number in there and look at the sign of the second derivative. The critical number was pi halves, so we want f double prime at pi halves. Negative sine of pi halves minus 2 times the cosine. 2 times pi halves was pi. So here's the tricky part again. Well, if the cosine of pi halves is 0, what's the sine of pi halves? 1. So this becomes -1 right here. All right, cosine of pi, -1. So when I take these numbers and combine them, I get a +1. The size of the number itself doesn't matter, but the fact that it's positive does. I got 2 little plus sign eyes, which makes a happy face. So that means my critical number is down there at the bottom of the smile. It's a relative min. So that's our conclusion. We've got a relative min at x's pi halves. Okay. So when we're not interested in the whole graph, we just want to know the behavior of the function at a single point, then the second derivative test will be handy for us. Okay,
Question.
yes,
So, why didn't you use the double angle?
I don't need to. I wasn't looking for the critical numbers. I was told that this is a critical number.
Okay.
So I just want to prove it by plugging that in, showing the derivative is 0. But if it said find all critical numbers,
How
then I
did you
would.
find the value to be 0 and of 2?
So you want to know how I got that number.
Yes.
So this is the same as the cosine of x minus 2 sine x cosine of x. Then the factor, common factor of cosine of x. And I get 1 minus 2 sine of x. Set each factor equal to 0. So here's where I get the cosine of pi halves to be 0. So this gives me x is pi halves and 3 pi halves. And every pi half thereof from there on out. This is where the sine is equal to a half. So some other critical numbers are sine of, give me a reference angle for sine of that angle is a half. What'd you get? 5 or 6 is correct. Then we got to move in the second quadrant. And then every 2 pi multiple of those. Okay, so there's a whole bunch of them. I just plucked that one out. But now if you want to test this one, minus the sine of pi 6 is a negative a half. Cosine of pi thirds is a positive 1/2. 2 times a half is 1, so negative half minus 1, it's negative there. So this one's going to give you a max.
So you use those trig identities whenever you're trying to solve for x.
Right.
Okay. Good to know.
Good to know. Okay. So we'll revisit the second derivative test later on in the chapter. So right now, let's bump over to section 4.4, and we're going to look for asymptotes of functions. For horizontal and vertical asymptotes of functions. The way. For the most part, we're talking about functions that are rational expressions that have these. Although we do have some functions that have asymptotes. The graph of y is equal to e to the x has a horizontal asymptote on its left end, right? There's a horizontal asymptote right there. The graph of y is equal to the natural log of x had a vertical asymptote at x is 0, because these are inverses of one another, right? So here's an example of a function that has a vertical asymptote. Here's one that has a horizontal asymptote. A vertical asymptote represents a discontinuity, and we can't take the log of 0. A horizontal asymptote represents tail end behavior, when x is a number way back here or way over here. to the left of big N or to the right of little n. If the graph starts approaching a horizontal line, that line's called a horizontal asymptote. Other than these two functions, some trig functions have vertical asymptotes because they're essentially rational expressions. So we're talking about functions that have the form, we will primarily is that how you spell that? Deal with functions of the form. So,
There's a
So there's a reason I'm studying nature, I can't spell.
yeah. You just have to kind of say it right. Primarily. That doesn't look right. Let's take some of this out.
And I know it's wrong.
That, you just gotta feel it. You just gotta go with it. And if you're not sure, just write real poorly.
Yes. So it can look like multiple.
That's right.
There were no little cursive I got used. 6
Squiggles.
years.
But didn't I tell you that in fourth grade I came in second in the class spelling bee? I'm number 2. TOO. I couldn't spell biscuit. I remember in second place in the word I couldn't spell.
Honestly,
Honestly.
BUIC.
What did you say, Jackie?
Wait.
Like this, and I always start with BU, and I'm like,
Wait, BISC.
It's like this. This. I don't know.
I
I say it wrong, so I know how to say it. Like
My
this.
gosh, why isn't it spelled the way you say it? It's a biscuit. Where's this dang Q coming from? Who even put Q in the alphabet?
There's a
There's no biscuit. C. There's a C. The C sounds like a Q sometimes. Right?
I
This-
don't know the spelling bee on drawer.
That's good.
Okay,
I
when
don't
I
even
say, if
remember
you
what
understand what I'm trying to say, then it's correct.
Yeah.
Yeah.
We had a Chinese graduate student one time, real good at math, but her students were complaining about her language skills. So she turned around and said, "Do not listen to what the mouth say, listen to what the chalk say." And she was right. Her words were beautiful. So with me, it's somewhere in between. I'm going to spell it wrong. I'm going to say it wrong. Just understand what I'm trying to say. Okay, if we have a denominator in a function, we have potential for dividing by 0, which makes this thing not defined. Where the function's not defined is where these vertical asymptotes come into play. So these functions will have vertical asymptotes where the denominator is 0, but the numerator is not 0, right? Because if they're both 0 at the same place, that just shows it's a hole in the graph. And we can eliminate that with a limit. But where the denominator is 0, but the numerator is not, is going to be a big old rip in the graph. Like the function f of x is equal to 4 divided by x minus 1. Has a vertical asymptote along the line x is equal to 1. What does the rest of the graph look like? What does the graph look like around that vertical asymptote? What does it look like near the vertical asymptote? Well, maybe the derivative will tell us. The derivative tells us almost everything about the graph. Let's take the derivative of this. Thinking of it as 4 times x minus 1 to the negative 1, and you can quickly take the derivative of the power rule. So we're trying to find out, what does the graph look like? We'll take the derivative. Using the power rule real quick. Bring the power down, raise it to 1 power less, multiply by the derivative of what's inside. And you get minus 4 x minus 1 to the negative 2 times 1. So you get minus 4 over x minus 1 squared. Well, that's telling me my derivative is always negative. If x is not 1, everywhere else the derivative is negative. Because my bottom is positive, top is negative. So f prime is negative for x not equal to 1. So I've got a graph that's strictly decreasing. Well, let's draw that. Let's put in the line x is equal to 1 right here. It's an asymptote. It's not going to cross that line because there's no x coordinate there, so there's no y coordinate there. How can the graph always be decreasing and not hit that line? Decreasing, so it's leaning like this. So when it's over here, it's going to stay over there and just kind of bend toward that line, right? Let's see, when x is 0, y is negative 4. So it's going to go through 0, negative 4. But other than that, it's going to be decreasing. Right? Doesn't have any max or mins. It's just always decreasing. It has to be decreasing over here as well. So if it's decreasing over here, it's going to be up here and bending away from that line. So it's going to do something like this. Two little hyperbolas there. Again, I've lied. This graph also has a horizontal asymptote. In reality, this one's going to be down here and stay down here. And this one's going to be up here and stay up here. We'll talk about horizontal asymptotes in a minute. Vertical asymptote is when the bottom is 0. But that's after the fractions in reduced form, because we don't want to identify where holes take place.
What did you just say about the holes?
Let me say it this way. Suppose I have f of x that function essentially is the same as that first function, but in disguise, kinda moved over a little bit, because x squared minus 3x plus 2 factors. What does it factor as? So you see the common factor of x minus 1? That would cancel, but geometrically it shows up as a hole in the graph. You can't cancel it unless we're away from 1. So there's a hole in the graph at x is equal to 1. There's a vertical asymptote at x is equal to 2. Okay, so the hole in the graph has a y value. If I take that factor away, now put 1 in for x. 4 over 1 minus 2 is at negative 4. So the hole occurs at 1, negative 4. The rest of the graph should kind of be the same. Here is, well, 1, negative 4, and then x is equal to 2. And then it should have the same shape. It's because I didn't do much but shift it over. So it's going to go down like that. And it's going to be up here. So I'm going to have a negative derivative as well. So if it has a common factor, it's not an asymptote. Common factor gives you a whole. Now, what makes, we can describe asymptotes with one-sided limits. In this particular picture, x is equal to 1 was the vertical asymptote. And I'm showing you that this end goes down as I come in from the left. So I would say as x goes to 1 from the left, the limit of my function 4 over x minus 1 is equal to minus infinity. The y values get big and negative. I say this with the right-sided limit. X is going to 1 from the right of 4 over x minus 1. It's big positive numbers. So when you have an asymptote, you're going to have one-sided limits that go to infinity, either plus infinity or negative infinity or some mixture of. So let's see if you can determine this. What are the vertical asymptotes? F of x is equal to 1 over x squared minus 4. Any ideas? There's 2 of them. There's 2 value of x that makes the denominator 0. X is 2 and x is negative 2. Let's see if you can use the derivative to answer the following questions. I want to know the behavior of this function as x goes to positive 2 from the left. I want to know what happens as x goes to positive 2 from the right. And now let's do the same with the negative 2. Come from the left and right, x is negative 2. And I think you can use the derivative quickly to tell you that. Because the derivative will tell us when it's increasing or decreasing. So take the derivative, maybe write it as x squared minus 4 to the negative 1. Take the derivative, and let's analyze the sign of the derivative. So bring the power down. Raise it to 1 power less, puts me a negative 2 power. Don't forget the derivative inside. And so when you simplify that, puts a negative 2x on top, x squared minus 4 squared on the bottom. So I get a critical number where the numerator is 0. That's at x is 0. The denominator is going to be 0 at 2 and negative 2. We need to use those as cut points, just in case this changes sign. But x is 0 is my only critical number. And then I've got an asymptote at negative 2 and at +2. So let's see what happens to the sign of the derivative. Always include your asymptotes when you check the sign of your derivative. They're not going to affect the sign of this derivative because the bottom is squared. Right? But if the bottom had an odd power, those asymptotes could possibly affect the change in sign. So let's plug some numbers in. If x is a -3, I get a +6 on top, a positive number on bottom. The derivative is positive there. If x is a -1, I get a positive on top, a positive on bottom, so it's still positive there. If x is a +1, I get a negative. If x is a +3, I get a negative. So my graph has to rise, keep rising, drop, keep dropping. So x is 0 is a relative maximum. Now let's see what that means to the graph. X is 0 is a max, x is 0 is a max, f of 0 is a -1/4. F of 0 is -1/4. So in here, between the two asymptotes, is it pretty obvious what it's going to look like? Rise and then fall, but not cross the asymptotes. Has to rise to the left of -2. So it's going to come in here like that, right? So this part of the graph is going to go up. Has to fall to the right of this asymptote. So if the graph is decreasing, it's going to have to do something like this, right? Rise, rise, fall, fall. Follow the arrows. And now you can look at the picture and decide the value of these limits. They're either +∞ or -∞. So look at x is 2 and tell me what's happening to the left of 2. You're looking at x is 2. What's happening to the graph to the left of 2? So this limit is -∞, right? What's the value of the infinity? I'm sorry, which sign on the infinity symbol when you're taking the limit as x goes to 2 from the right? Look at the picture. You're hugging that line on the right-hand side of it. So it's going up to positive infinity, right? Going up, 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 up. We're coming in this way. Okay, now look at the asymptote at x is -2 and on the left of it. Am I getting big positive y values or big negative y values? Positive, these are these guys. And on the other side, -2 from the right. Describe the y values. Negative infinity. Okay. So the y values become infinite around a vertical asymptote. All right, let's look at horizontal asymptotes. So, horizontal asymptotes. We want to know if all of the y values approach a certain y value when x is a really big number, either a big negative number or a big positive number. We want to know if the tail ends of the graph approach a y value, a horizontal line. Right, so the graph might have some sort of graph. Might just put a horizontal line in here. All kinds of things can go on in between. I might have a graph that does all kinds of things, but way out here at the end, it starts acting like that horizontal line. And that horizontal line is a horizontal asymptote. Same deal here. It's a limiting value when X is a real big negative number or a real big positive number. So we find that by taking a limit as X goes to infinity. Usually it's a fractional expression, a numerator over a denominator. If that occurs, then the line y is equal to L is a horizontal asymptote. Here I wrote a big positive number, it could be a big negative number as well. So you would look at limits to plus and or minus infinity. So let's look at this. Let's look at y is equal to 1 over x. What happens to this? That is y, and x is real big. What is y when x is really, really big? Maybe you got $1 and you want to share it with 1 million friends. How much do they all get? Essentially nothing, right? And say 1 over infinity is going to be considered to be 0. At least the limit anyway. Right. So if we can agree to that, then we can figure out horizontal asymptotes. The function that we just had. F of x is 1 over x squared minus 4. Now imagine the y values when x gets bigger and bigger and bigger and bigger and bigger. Whether it's a big positive number or negative number, it doesn't matter because we're squaring it, which makes it even bigger. Subtracting 4 didn't put a dent in it. So this is behaving kind of like that, right? 1 over infinity. Agree? As a horizontal asymptote of y is equal to 0. That's the x-axis. Because the limit as x goes to either infinity or minus infinity, since this is squared, it doesn't matter, is 0. 1 over a big number, so that number keeps getting bigger and bigger and bigger and bigger, 0. That's going to be true even if I start messing around with powers. Let's look at something like that. I want to know what that limit is. Now that one's not as easy to eyeball as this one is. 1 over a big number is 0. But here, x is getting big, so I'm going to have a big number on top and a big number on bottom. So I'm really not sure what's happening. So what I'm going to do is I'm going to introduce terms that look like this. I'm multiplying that fraction by 1. The highest power of x in each case is x to the first power. So what I'm going to do is multiply top and bottom by 1 over x. And I'm allowed to do that as long as x is not 0, and it's not. It's going to be a big number. So I'm just going to do this algebra right here. So that I'll have terms in there that look like this when I distribute that. Distribute that x now through there, and I'm going to have 4x over x. That'll simplify to 4. Plus 3 over x. And then I'm going to have 7x over x. That simplifies to 7 minus 1 over x. So when you're taking this limit, here's what you see in your head. We'll put it in a cloud because that's your thinking cloud. You have 4 plus 3 over something that's infinitely large. 7 minus 1 over something that's infinitely large. And we agreed up here, dividing by something large will make that term go to 0. So the 3 over infinity, the 1 over infinity are acting like zeros. And all we're left with is 4 over 7. It's that easy. It's even easier. Okay. Let's look at 5x divided by x squared plus 4. We should call that f of x. I want to know the horizontal asymptotes. I take the limit as x goes to infinity. If I want to use that same idea that I had a second ago, I'm going to scale this down by dividing every term in here by the highest power on x. So this time the highest power on x is x squared. So let's multiply top and bottom by 1 over x squared. It's the highest power of x that controls the behavior of the function when x is a large number. That's what motivates me to do this. And I have to multiply by 1 so that I have an equivalent fraction. And so when I do that, I get the limit as x goes to infinity. I'm going to have 5x over x squared. Then I'm going to have x squared over x squared plus 4 over x squared. That's going to reduce to 5 over x, 1 plus 4 over x squared. So put your little thought bubble in your head. 5 over a big number is going to go to 0. 4 over a big number squared goes to 0 even faster. So all that's left down there is a 1, but I got a 0 on top, a 1 plus 0 on the bottom. So that gives me the line y is equal to 0 is the horizontal asymptote. Now, if you think about those steps that we did just for these 2 examples, we can probably generalize for all examples. Even if these were x squareds or x cubes or whatever, if I have the same power of x in the numerator as I do the denominator as the highest power of x, look what we get as the limit. Where these numbers come from. Right? If these were x squareds, I'd have x squareds here. And the same deal happens. The lower degree terms vanish. What's left of the numbers in front of the same power of x. So if the degree on top is equal to the degree on the bottom, this limit should always give us the ratio of the coefficients of the highest powers of x. In this example, the bigger degree was on the bottom. So the bottom of this fraction grows faster than the top. So when these are big numbers, the big numbers are going to overwhelm the numbers in the numerator, causing the overall fraction to go to 0. What if it were upside down? What if I had the x squared on top and the 5x on the bottom? Then the numerator has bigger power. It keeps growing, the denominator can't catch up. So the y values keep getting bigger and bigger and bigger. So that after a while, we won't even have to do these steps. We just look, degree on top is the same as the degree on the bottom. We take the ratio of the coefficients. If the degree on the bottom is bigger, we should always get 0 as our horizontal asymptote. And if the degree on top is bigger, we're not going to have a horizontal asymptote. The ends will just keep growing and growing and growing, either in a positive direction, negative direction, or some mixed match. And so I'll write that for you next time on the board, but practice taking some limits. I've got some limits put up there for you in Weber. And thus endeth another 2-hour day. You're losing it for me over there. That's through section 4.4. I'll do a few more examples next time and I'll write down what I said here. All right, time for me to switch classrooms.